Okay, let us just continue with what we have said. Last time we have just said about this ketone effects, 2 alkyl ketone effect, 3 alkyl ketone effect, and then I said there is 4 alkyl ketone effect also, but I did not elaborate on that 4 alkyl ketone effect. In other systems, another interesting system is, instead of a ketone, if you have a double bond here, suppose, and these double bonds will have substituents at these positions. Okay. Now, in that case, it will be also very similar because of this double bond. Now, this equatorial hydrogen will be eclipsing this one, that is no doubt, but this is quite close to this R2 on this side, and the equatorial hydrogen here, that will also be quite close to R1. But if it is hydrogen, it does not suffer much interaction. But suppose this is not hydrogen, if the R I place here and if the hydrogen is here, then what happens? There will be steric compression between R and the R2. Okay. And that steric compression will be reduced if it goes into this form. If it flips and goes into, this is R2 R1, but now this R is in the axial position, where this type of steric interaction is not present. So, this is cyclohexane alkene system. I can make the system here for you. This is the cyclohexane exocyclohexene. So, cyclohexane attached with the exo double bond, and if you see that there are now, if I put this group in the equatorial position. So, what I was pointing out is, sorry, this is just coming up, yes, this is the cyclohexane alkylidine system. Now, this is the group which is suppose R1 or R2, and this is the equatorial group at C2. Okay. So, you see how close are they. So, they are now sterically crowding each other. Okay. Now, if you invert it, if you now do the flipping, so you see this is the double bond going away from this group now, because this group is in the axial position. So, axial orientation, you do not have this strain because they are far apart now. The groups attached to this exocyclic carbon is no longer in proximity with the axial alkyl group. Okay. Now, this is what is called. So, these systems also will have considerable amount of this type of this axial way of axial conformer. And like your 2 alkyl and 3 alkyl ketone effects, this has also a name. This is called allylic 1,3 strain. Allylic 1,3 strain, why? Because this is your, suppose this, because the strain is between the substituents attached to C1, then 1, 2, 3 and attached to C3. So, because it is the strain between the substituents attached to C1 and C3, so this is called allylic 1,3 strain. Okay. These are some interesting features. They are very important while dealing with reactivity of molecules. Okay. So, we have seen so far, we have just been dealing with the preferred conformation of different. First we did acyclic systems, and then we studied the some other acyclic systems, then the cyclic systems and special cyclic systems like cyclohexanone or alkylidine cyclohexane, that means cyclohexane with exocyclic double bond. And we have seen that according to the situation, the preferred conformation varies. Okay. The factors that need to be considered while drawing the preferred conformations are, first of all, the torsional strain, then the steric strain. Torsional strain is also, the eclipsing strain is similar to the torsional strain. and then the steric strain, that is the size effect. Then you have the hydrogen bond effect, you have dipole-dipole repulsion. So, these are the things which you need to consider while arriving at a conclusion to draw the preferred conformation of a molecule. Okay. Now, this stereochemistry, what we have learned so far is what is called static stereochemistry. Means we have only checked the conformation and we have only checked the energy differences between the possible conformers, and that is it. We didn't say anything about the reactivity of these molecules. Means this conformation analysis has two aspects. I gave you the definition of conformation analysis. One is conformation analysis deals with the variation of energy as you rotate the system, as you rotate around carbon-carbon bonds, as you flip a system like cyclohexane, then how the energy changes. That is what is called there is one type of conformation analysis with respect to energy. There is another type of conformation analysis which is the which takes care of the reactivity. That means how the reactivity pattern of a molecule changes with different conformations of a system. Okay. Now, this is what is called dynamic stereochemistry. So, now the topic is going to change. Now, dynamic. So, what we have seen so far is static stereochemistry. So, the molecules are just seen in isolation. There is no partner to react with. We just check the energy and the different types of interactions that are present in the system. Now, the next question is how these different types of interactions and different types of conformers are going to affect the reactivity of the system. So, this is what is called dynamic stereochemistry. Dynamic means what is the other way to tell it is as conformation and reactivity. So, now the reactivity, that means the reactivity issue is brought in, that how does the different conformers affect the reactivity of a system, conformation and reactivity. Now, this conformation and reactivity concept, that actually conformation also dictates the reactivity, was put forward by a British scientist very elaborately. His name was Sir Derek Barton. He was at Imperial College, and he wrote a paper in a journal called Experientia that was very famous those times earlier. So, he wrote the conformation analysis versus reactivity of cyclic systems when there are different types of when the number of cycles varied. So, he studied the cyclohexane, the decalene, and then even the bigger ones like steroids and terpenes, because they have similar kind of decalene systems. Okay. His name was Barton. Now, before Barton, there was another professor from Norway. He first pointed out, so if Barton has elaborated the whole concept, but the whole thing started with a person called Odd Hassel. He was a Norwegian scientist, and he was studying the pKa values of cyclohexane carboxylic acids. Okay. Now, cyclohexane carboxylic acids, if you put a tertiary butyl, suppose, I am not very sure whether this was the example, but the essence of his study is can be described with the help of these molecules. So, he was studying the pKa of cyclohexane carboxylic acids. He took one molecule where the carboxy is in the equatorial position, and he took another molecule where the carboxy is in the axial position. But in order to lock the system, see, you need a locking group. I already told you tertiary butyl is a locking group. It prevents the molecule to flip. So, there is no interconversion between axial carboxy versus equatorial carboxy. So, he was trying to measure the pKa. Now, interestingly, what he observed is that the pKa of the two compounds are first of all not same. So, this is a very interesting thing that where the electronic effects obviously will be similar in both the cases. The electronic effects will be the similar because the connectivity is same. So, and the T butyl group is far away. So, its inductive effect, the electron donating effect cannot reach this carbon. Even if it reaches the carbon, it reaches this carbon to the same extent like this molecule, in this molecule also. So, there is no electronic effect that can say that there will be a pK difference, but he found a pK difference, and what he found is that this is a stronger acid than this one. So, this is a weaker acid. So, weaker acid means higher pKa. So, this is higher pKa and this is lower pKa. Okay. So, this is stronger acid. So, that is the starting point of conformation and reactivity concept. So, that means the property of this molecule, the reactivity as an acid of these molecules depend on the conformation, whether it is adopting an equatorial CO2H or an axial CO2H. This was studied by Hassel. So, then what was the explanation? The explanation was that the pK is measured by the dissociation constant. So, it dissociates into the carboxylate. Now, the more the carboxylate you have, that means more dissociation you have, that means the acidity will increase. Okay. Now, this is the carboxylate in the equatorial position, this is the carboxylate in the axial position. Now, you know that there is a huge role that is played by the solvent in stabilizing this anionic species, okay, this carboxylate. So, this carboxylate will be solvated, will be stabilized by solvation, and this will also be solvated. Now, the problem is the solvation of this axial carboxy will be little bit hindered because of the presence of these hydrogens. Okay. So, because of the presence of these hydrogens, solvation will be less here. That means, solvation stabilization through solvation will be less here. This, on the other hand, because it is in the equatorial phase, so there is no such interaction can be conceived, because there is no 1,3 diaxial interaction. So, solvation will be more here. That means, stabilization through solvation will be more here. That means, dissociation of the corresponding acid to the carboxylate, that means, the equatorial acid to the carboxylate will be more than the dissociation of the axial carboxylic acid to its carboxylate. So, that is due to the problem of solvation in the axial carboxylate, because solvation means size increase, and size increase means more or greater steric repulsion. Okay. So, that is why this dissociates more, that means, the equatorial carboxy, and that became that has got the higher acidity, that means, lower pK. So, that is the starting point of the whole story, but this is a thermodynamic parameter, the pKa. What about when the reactivity, we say this is a kind of thermodynamic parameter pKa, that is the acidity, but we have to also bring in the kinetic parameter in order to study the reactivity of these type of molecules which can exist in different conformations. Okay. So, before we will discuss some of the issues that Barton had dealt with. One of them is conformation and reactivity. One example is, suppose I want to oxidize two compounds. One is cis 4 tertiary butyl cyclohexanol and the corresponding trans compound, the trans 4 tertiary butyl cyclohexanol. If I want to, so which one will oxidize? So, oxidation profile, that means, which one will be oxidized more or at a faster rate. Now, we are bringing in the kinetics, okay, at a faster rate than the other. Okay. Now, you know that this is an alcohol. Alcohols can be oxidized by chromic acid. Suppose we are using chromic acid. In fact, Barton was studying the chromic acid oxidation of the cis and trans 4 tertiary butyl cyclohexanol. Okay, now, in order to arrive at an answer, so what we need to do? We have to first draw the molecules. So, this is your cis tertiary butyl cyclohexanol, and the trans one is this is the alpha OH. Okay. Now, from the planar system you cannot actually arrive at a conclusion. So, what you have to do? You have to draw the correct conformation of these systems. Now, these are locked systems. Okay. So, one good thing is that they are locked systems. So, there is no question of flexibility in these molecules. They are locked because of the tertiary butyl. So, there will not be any interconversion between the equatorial wedge or the axial wedge. Okay. So, this cis compound has an axial wedge, and the equatorial compound will then have an this trans compound will have an equatorial wedge. Okay. So, these are the two conformations. Now, if we know that the chromic acid oxidation, or if you do not know, let me tell you that the chromic acid oxidation actually takes place via formation of. So, this is the chromic acid, the anhydride CrO3. So, the first step is that which attacks the chromium, and this goes to the, say this is in the +6 state, sorry, +6. Okay. So, first the which attacks the chromium and it becomes RCH which, because it is done in sulfuric acid. So, there will be lot of proton sources, double bond O and double bond O. Okay. So, then, so this is what is called the, sorry, this is OCH, CrO. So, RCH2O, this hydrogen will be lost after the nucleophilic attack, OCr OH and then Cr double bond O, Cr double bond O. This is what is called a chromate ester. Why ester? Because this is basically chromic acid and an alcohol. So, that makes a chromate ester. So, the next step, so this is not the oxidation. Remember, chromium is still in the 6 oxidation level. So, in the oxidation chromium will be reduced. So, this is the first step, and the second step is that a base which is most likely to be the water that is present, little water that is present in the system. So, it comes, or it could be bisulfate also if there is sulfuric acid. So, that comes and takes this hydrogen as a proton, this comes here, and now the chromium is reduced and gets the 2 electrons onto it. So, chromium gets to the +4 state, and then it disproportionates into +3 and +6. Okay. But that is the more important issue is that this gets oxidized. Okay. There is a creation of a double bond O in the system. So, this gets oxidized, and that means the rate of chromic acid oxidation now, it involves 2 steps. Now, which is the rate determining step? That is the very important issue here. Okay. Now, what has been found that this is a very fast step and this is the slow step. So, if this is the slow step, that means the breakdown of the chromate ester is the rate determining step. So, breakdown of the chromate ester is the rate determining step. Okay. So, this is on the side. So, we know that first this will form a chromate ester. So, RCr double bond O RCr double bond O OH, and then this H, equatorial H, has to be taken up by the base to form the cyclohexanone, and in case of the axial wedge, equatorial wedge, sorry, that was we started with the axial wedge. So, axial chromate ester, decomposition of the axial chromate ester, and that will give to the tertiary butyl cyclohexanone. This will also lead to tertiary butyl cyclohexanone, but via an equatorial chromate ester, O Cr double bond O OH and then double bond O, and then this axial hydrogen has to be picked up by the base, which is water here, and this is the mechanism. So, you have a tertiary butyl. So, that goes to the same compound as this. So, final product is same. So, now the question is which one will be oxidized at a faster rate. First it was first Barton gave an explanation which relied on the abstraction of this equatorial hydrogen versus axial hydrogen. So, he argued that the axial hydrogen will be more difficult to pick up, because the water has to come. I showed from this side, but you see there are axial hydrogens. So, basically if the water approach of the water to abstract the hydrogen will be more difficult, because this phase is sterically hindered than the approach of water to abstract the hydrogen from the equatorial side. That was Barton's explanation. So, he said the equatorial, the essence is that the axial hydroxy, that means the cis compound, cis 4-tertiary butyl cyclohexanol, should be oxidized faster, at a faster rate, because it involves the abstraction of an equatorial hydrogen, which is the more accessible. Okay. And this is oxidized at a slower rate, because it involves the abstraction of a hydrogen at the axial position. However, later on it was found, we are not going into very big details, but later on it was found that this type of explanation was not correct. The actual explanation, after studying several other compounds, different substituted cyclohexanes, Asian Mosher, another scientist, he gave what is called an explanation based on what is called steric acceleration. I think you will be amazed to know this word, because I am sure up till now what you are told that steric factor is always a very bad thing, it slows down the reaction, But this is an example where Asian Mosher is telling, he is a Swiss scientist. He said that the reason that this is oxidized at a faster rate is what is called steric acceleration. That means, here the rate determining step is the second step, that means decomposition of the chromatester. Now, the chromatester, this is very big. That axial group was earlier weak. When it forms the chromatester, it becomes big, and now it is suffering from enormous steric compression. However, formation of the chromatester is not the rate determining step. If that was the rate determining step, then this would have been slow, but this is a very fast step, and so it is formed irrespective of whether there is increase of steric compression or not. Now, the steric compression has increased. So, now the decomposition, in the decomposition step, that means the decomposition of the chromatester, now the chromatester will decompose very rapidly in the axial chromatester, because there is enormous release of steric strain. So, this is what is called, he called as steric acceleration. That means, the steric factor or steric compression is accelerating the next step, thus the oxidation, okay, the loss of the hydrogen. So, it is not that the hydrogen is more accessible, the accessibility of the hydrogen is not the factor, it is the release of the steric strain, which is much more in the axial compound, axial chromatester, than in equatorial chromatester, where it does not suffer from such type of strain. So, there is no steric strain release in this case. There may be some, but much not to the extent in the axial that is present in the axial isomer. So, now this will be, that is the reason, due to steric acceleration, this this axial wedge is oxidized at a faster rate. Okay. There are again very similar examples where there is a difference. So, I have given you a difference between the pK of the carboxylic acids when they are in the axial and the equatorial positions. Next, I have talked about the rate of oxidation of an axial alcohol versus an axial equatorial alcohol. Now, I will tell you a third example, which is the saponification of an ester molecule. in a cyclohexane system if the ester is in the axial position or in the equatorial position. So, what is the rate? So, again I take two compounds. See, tertiary butyl is always required, so that equilibration between the axial and the equatorial does not take place, because we are comparing the rates of the axial and the equatorial systems. So, the whole thing will become complicated if there is equilibration between the two. So, to stop that equilibration, you have to put the tertiary butyl group. Now, what we are talking about? The problem is that we are talking about the hydrolysis of an ester when it is in the axial group versus the hydrolysis of an ester when it is in the equatorial position. Okay. Let us see, because I said equatorial because I know that if I want to draw this into the perfect in the conformation, in the Packard conformation, so this will be the equatorial one and this will be the axial one. Okay. The question is which one will saponify faster? Saponification means hydrolysis in a basic condition. Okay. So, if I hydrolyze it under a basic condition, that means OH minus is the nucleophile. Okay. So, which one will hydrolyze at a faster rate? Now, this is interesting. Unlike the axial alcohol versus equatorial alcohol, now it is the other way around. The equatorial acetate, that the equatorial ester will be hydrolyzed faster as compared to the axial ester. Now, what is the reason here? The reason is that again the mechanism has to be brought in, that what is the mechanism of saponification. Take a very general case RCOO, O say OAME, and if you add alkali. So, the first step is this attacks, this goes back. So, RCO minus, then OH, then OME. So, this is the tetrahedral intermediate, and then so this is the first step, and the second step is expulsion of this OME. So, you get RC double bond O OH plus OME minus, and then there is mutual exchange of the hydrogen, because this is a stronger base and this is, so that will abstract the hydrogen from here, and this is the weaker base. So, it will be the carboxylate plus methanol. So, that is the mechanism. Now, this is a very fast step. This is also very fast step. The rate determining step is this one, the attack by the OH minus. So, this is the slow step, that means this is the rate determining step. So, what happens in the rate determining step, that will guide the process. So, when OH minus attacks, I again remind you, that is the rate determining step. So, there will be increase of steric bulk in the axial system. Okay. O minus, OME, and then OH. Okay. Then there is these hydrogens. So, there is this increase of steric strain due to the OH minus attack, and that is the first step, that is the rate determining step. So, this will be slower as compared to the attack by this OH minus into the carboxylate, into this ester carbonyl, because there is, even if the size increases, there is no increase of steric strain here, but there is increase of steric strain here. So, this will be slow and that will be fast. So, here interestingly, the breakdown of this tetrahedral intermediate is not the rate determining step, and that is why this whole result has gone just the reverse way. Now, the equatorial ester is hydrolyzed faster, because the step where the steric size increases, that is the rate determining step. In chromatic acid oxidation, the step where the steric bulk reduces, that becomes the rate determining step. So, that is why we see different results in both these systems. Thank you.